Hello, I will be going over the quiz that was taken on Monday and Tuesday of the week before the final, in which we looked at different acid environments for the protons on two different molecules, and then I will work on several of the sapling problems worked on in class, a few let's thinks, and then a summary of features 1, 2, and 3. And so if you would like to see a summary, that's going to be happening at the end of this video in slides 9, 10, and 11. Right, so this problem asks if we to rank the acidity. We see 4 different protons, so let's do that. The first thing to notice here is that the fourth carboxylic acid is 1 carbon away from a carbon with a withdrawing group, while the 1 and 2 are 2 carbons away. So that's going to play a big role in determining which proton is most acidic. So we're going to go through and say, look at the features, and we see that they all have feature 1 because all of the negative charges of the conjugate bases that would be made will all be on oxygen. But 3 is definitely going to be least acidic because it has no feature 2. And feature 4 is going to be the most acidic based on feature 3, which is going to be bond polarization. It's 1 carbon closer with the electron OH group than 1 and 2 are. So 4, 2, and 1 all have features 2, which is going to be resonance, the single bond, double bond, and that's going to stabilize it more than OH. So that's the argument that 4 is going to be 3 is going to be the least acidic, and 1, 2, and 4 are going to be more acidic, with 4 being the most out of that 3 due to the bond polarization, the higher bond polarization. So we would pick B. So in question 2, we've answered this question already, but so the key feature, like what accounts for the differences, and so if we look at the conjugate bases that are going to be formed, we're really comparing in features 1 and 2 the top conjugate base here that's 2 carbons away versus feature 4, which has only 1 away. This is going to be more stable because of feature 3. Features 1 and 2 are both the same, so we will pick C. And D and E are wrong. Okay, next question, new molecule, and it asks again to rank the acidity of the different protons, and so let's do that. What we're going to do is look at the different conjugate bases that are going to be made. So group 1 is going to look like this, has 2 chlorine withdrawing groups. And we're going to compare that versus 3's, which just has a carbon attached to here. And then we have 1, 3, and 2. So 2, we see we have electrons being donated by the different carbons. That's going to destabilize 2. 3 has only 1 carbon, and 1 has electron withdrawing groups, which stabilizes. Sorry about that. Getting used to this. So, okay. So we see 1, 3, and 2. Here are the 3 carbons. So the carbons are being donated into 2, right? So it's destabilizing the oxygen. While 1 has electron withdrawing going out, so that's going to stabilize 1. So the least stable conjugate base is going to be 2. The most stable is going to be 1. So most stable product is going to result in 1's conjugate base, and the least stable in the 2. So when we see the rankings, we would pick A. The least stable product would be the least made, and it would be the least acidic because it's a product. Okay, and this is what accounts for these differences. So we can see that electron donation increasing the potential energy of the conjugate base, raising potential energy due to electron-electron repulsions, means the less stable product. Then you have electron withdrawing groups that are going to reduce electron-electron repulsions and make it more stable. So we would pick feature 3. This is the bond polarization argument, and so feature 3. Okay, so this is a question we did in class. So we're asked to assign acidity based on 4 different functionalities in the molecule. So let's do that. So we see in C, when we circle C, the conjugate base that's going to be formed from a proton being lost in C is going to be the negative charge on carbon. The one on B is going to result in a negative charge on nitrogen, right? It's going to, each of these cases, lose a proton. This is the conjugate base we're talking about. D is going to have oxygen with a negative charge. And A is also going to have a negative charge on oxygen, but it's going to have a single bond, double bond. Ranking them this way, we see that we have a nice potential energy ordering where carbon, with a negative charge on carbon, is going to be the least stable, it's the least electronegative, and then the additional resonance on oxygen is going to make it more stable. So keep in mind that the general reaction that we're considering is the weak acid reacting to make its conjugate base plus H3O plus. So the more stable this conjugate base is, the more H3O plus we're going to generate, the more acidic solution we're going to have. So what we say is that site that makes the most stable base is going to make the most acidic proton, and we connect it back to the acid. That's why we're circling these areas, because we're linking the eventual conjugate base, the conjugate base made with the loss of the proton and a negative charge on that atom, makes it the most stable. So when we rank these, we see that C, which has the carbon, is going to be the least acidic, is the least stable product. It's not going to make very much H3O plus. And if we go in that ordering, we see that A would be the most stable. We get the most stable product. We should get the most acidic solution when that reacts, when that part of the molecule reacts with water. Okay, so for base, we just have to make the same argument, but it's going to be slightly different. So let's do that. So the potential, so first of all, we're going to order the potential energy, and we're using feature 1. We see that oxygen is more electronegative. It's going to be more stable than nitrogen. So we see that we would place that at the bottom. Then we have nitrogen with a single bond, double bond. Then we have a nitrogen with only 1 carbon bonded to it, and then a nitrogen with 2 carbons bonded to it. And so this is going to produce our energy ordering, right? Because we see first we have feature 1. So feature 1 is going to distinguish oxygen for us versus all the nitrogen. So it's going to be the lowest potential energy because it's the more electronegative. So oxygen is more stable than nitrogen, less basic. And what we're going to see in general for bases is that the more stable the base, the less basic it is, because base now is a reactant. So their general reaction is base plus water to make the protonated base plus OH minus. So the more stable, the less likely to react, right? That's our story for bases. So now we just have to look at the stability, and we would say, okay, well, we'll also see that Kb is going to increase with increasing instability. So the more unstable, the more likely it is going to react with water. We see that the nitrogen with 2 carbon donations are going to make a very reactive nitrogen versus one with only 1 carbon, or if there's a single bond, double bond. So if we make the energy ordering, it would go as this. B would be the least basic. It's going to be the most stable, and C is going to be the most reactive, which will make it most basic, have the higher Kb. Okay, so that's the argument. I mean, that's our general argument for acid and base. So you want to make sure you feel comfortable with those 2 arguments in slides 3 and 4. So here, so when we combine them, we now need to evaluate the two different bases, right? So here we have a general chemical reaction. Let's take a look. We have an acid plus a base, making a base plus an acid. So the acid-base conjugates are OH minus linking to water, and then acetylide with its acetylide base. So the two bases that we're looking at are OH minus versus CH minus. These are the two bases that we're asked to compare because the other two substances are acting like acids. So when we do the evaluation, here there are different, the negative charges on different atoms that definitely triggers feature 1. O minus is more stable than C minus. Since O minus is more stable, we consider it a weaker base. Most stable. So we consider this, so this reaction is going to be reactant favored because the weakest, most stable base is in the reactants. The strongest base, least stable, are in the products. So that would result in this being, there just be more of this substance because it's the least likely to react. And we would see K is less than 1. Alright, so here's another group that we did in class. So in case we went through this too quick, we want to hear some notes. So we're going to take a look at the first one, and so we see that there's a carbon donation at this in the products of the base. This is going to destabilize the base using feature 3, right? So feature 3 says that that's going to destabilize the negative charge on the oxygen because the carbon attached to it is going to put in electron density, increasing electron-electron repulsions. That is not present in the other base in the reactants. This is going to be the most stable. We would consider this reactant favored with K less than 1. In the second reaction, we're now comparing, we see in the products that there's feature 1 is going to be the same, right, as it was above. Negative charge on oxygen, negative charge on oxygen. But now we have a single bond, double bond in the products. That's going to stabilize, the stabilizing feature 2 with delocalizing electrons. Potential energy goes down, there's less electron-electron repulsions, and we can also make the entropy argument that the entropy increases favoring products because the charge density on the products decreases. There's less organization of water, so there's higher entropy on the product side. So using the energy argument and entropy, we would consider the products to be more stable and more entropically favored, product favored, K less than 1. And then for the last one, we're comparing this group here, which we see that there's a feature 1 analysis that there's nitrogen with the negative charge is definitely going to be less stable, better base than O minus. It's going to be a much better base, which means that it's less stable. So we see that, and also feature 2 because of the single bond, double bond in the reactants. So really for both reasons, we would pick reactant favored. The base in the reactants are going to be much more stable because of the O minus negative charges on the most electronegative element, and then feature 2 stabilization. Okay, there's another question here in sapling. So we're looking at the difference between O minus versus S minus. So this is a feature 1 analysis. We're looking at 2 different atoms with a negative charge on it. So O minus, so entropy reduction. Right, so what happens is the entropy is greater where the negative charge is on sulfur. That's going to be entropically favored because there's less organization, charge density goes down, and it's going to be more favored. So we would see here that, so O minus is going to have the highest charge density, so we would say that D is going to be the weakest base, most stable. D is going to be the weakest. This is likely to be product favored since the weakest base is in the products. K would be greater than 1. Right, so here we have, so let's just, I think sapling wanted to put a hydrogen there. So now we're looking at 4 different molecules. There's not a chemical reaction amongst the 4. We're looking at these 4 and saying identify the strongest acid in the group. So we're going to identify the strongest acid. We definitely are going to be comparing CH which is in B and C, which versus NHs. So NH is always going to be more acidic than CH. N is more electronegative. The negative charge that will be placed on the atom will be more stable with nitrogen than carbon. Right? So we're really comparing a nitrogen with a single bond double bond versus the nitrogen with two single bonds. Let's keep in mind that the nitrogen with the single bond double bond is always going to be more stable as a conjugate for feature 2 than if it was just single bond, single bond. So we would say that if we're looking at acidity, which means a negative charge will be placed on the nitrogen, it's going to lose the proton, that the most stable base is going to be the single bond double bond. And we would pick D. Strongest base is going to have a slightly different argument, but it's the same argument. Because what makes the single bond double bond most stable as the conjugate base, making it more acidic, will also make it least basic. So the strongest base is going to be the nitrogen, of course, not the carbon, but the nitrogen with the lone pair that is going to react mostly with water. That's going to be the one that's most unstable. It's going to be single bonds only. And so we would say that this would be the case where deciding between single bond, double bond versus all single bond, the strongest base will be the second degree amine. The carbons are destabilizing the electrons. These are unstable, most reactive, and we would pick A. Okay, so that's a review of the slides and quiz that were discussed in class. I just want to bring up a nice summary of the different features and how they interact with the different acid-base behavior. You get a lot of questions based on the features, so let's just talk about it. So feature 1 is used when comparing two different atoms, right? So if it's the same row, we look at the most stable, same row, that means the most stable base, right? The most stable base is going to be the most electronegative atom. But if we're going down a column, entropy plays the dominant role, and so we'll see that the largest atom will be the most favored, will be the most stable base. Due to solvent effects, there's less loss of entropy. So feature 1 had this argument. You want to make sure that you feel comfortable with feature 1 because it's usually the major discrimination. So why is one more acidic than the other? They're different atoms. This is the feature to use. Okay, so feature 2 involves the delocalization of charge and resonance that occurs with single bond, double bond combinations. So if the atom that has a single bond to a carbon, then a double bond, the conjugate will always be more stable. Right? So any base is going to be more stable. It doesn't matter. It's just all bases will be more stable if there's a single bond, double bond than if there were only single bond combinations. Okay, so this is due to the reduction in electron repulsions, making potential energy go down, making it more stable. And then the entropic reason is lower charge density, less entropy loss when the charges go into solution, and so it's always going to be more stable with the delocalization of charge. Okay, and then feature 3 is bond polarization. And so these are atoms that are attached to the carbon that is attached to the basic or acidic center. So if there are atoms that are more electronegative than carbon, there will be a pull of electron density away from the atoms near the base center or acidic center. This is going to lower the potential energy of the base. It always lowers the potential energy of the base, so it's going to, as a product, it's going to affect the products as a reactant in basic behavior, and it's going to be affect the products in the acid behavior. So if there are more carbons bonded to the atoms next to the base center, then the base is going to be destabilized. And so that means acidity decreases, right? So acidity decreases because the conjugate base is now less stable. And so we would say that pKa would increase and Ka would decrease if there are more carbons bonded to the basic center. While basicity increases, right? That makes it more unstable, the base. That makes the reactant is more reactive. pKb increases, pKb decreases. So this is a really important to feel comfortable about the applications. The quiz has a nice analysis based on that. So I would use this information to answer the quiz if you have any questions. So good luck. This is all the important major ideas that are in Unit 6, Module 3. Please make sure you feel comfortable with them.